My name is Dan Siegel. I'm a historian of science in the History of Science department at UW. And I'm going to be talking to you today about scientific method from the point of view of history and philosophy of science. Scientific method is a difficult question. And many historians of science want to say there is no such thing as the scientific method. Different scientists in different times and places go about science in different ways. Philosophers of science are a little bit more willing to make generalizations, but it's still a complex question even if one is willing to make generalizations. Philosophers of science, some of them have decided that one can classify scientific method into three ideal types. And here's a little visual aid for the ideal types of scientific method. There's the empiricist, rationalist, and hypothetical approaches to science. Now, these are ideal types. And if you look at the scientific practice of any given scientist or group of scientists, one finds a mixture of these three ideal types. So what I'd like to do is introduce you to each of these three types and then talk about how they've been effective through the history of science. First of all, the empiricist methodology. And the spokesperson for this methodology in during the scientific revolution, when modern science started, that is between 1600 and 1700, Francis Bacon was the spokesperson for this point of view. Empiricist comes from a Greek word meaning experience. And so this is an approach to science that says that science is based on experience and observation and experiment. And the image of the scientist that goes with this methodology is the person in the white lab coat who has a clipboard and writes down lots of data, observes lots of things, and writes it all down, and then organizes it and tabulates it and comes up with generalizations on the basis of this. For example, if I wanted to decide whether or not all apples have seeds, I would collect different classes of apples, Macintoshes and Winesaps and Golden Delicious and so on, see if they all have seeds, collect apples from different places, Washington State apples, local Madison apples, maybe buy some at Kohl's and some at Kopp's and so on, and then I'd sit down with all of my tabulated data on all these apples with seeds and might come up with a generalization that all apples have seeds. And Francis Bacon thought that this was going to be the way to do the new science at the beginnings of modern science. And the good thing about this way of doing science would be that it would avoid prejudice. You would come with a clean, open mind, and you would just be guided by experience. If one looks at the history of science, perhaps the most Baconian, and this brand of science, the empiricist brand of science, is called after not its inventor, but its great propagandist, Francis Bacon. It's called Baconian science. So one of the great examples of Baconian science in history is taxonomy, that is classification of plant and animal species, very much a business of observing and recording and organizing these observations. The French biologist Georges Cuvier said the purpose of biology was, in French, nommer, classer, et décrire, name and classify and describe. So that's a very empiricist Baconian science. but it does have its limitations as a scientific method. Classification is not always straightforward. One of the examples I like to use is the problem of the giant panda. Is it really a raccoon or is it really a bear? Well, if you look at its coloring, the black eye patches and so on, it sort of looks like a raccoon. On the other hand, if you look at its general size and shape, it looks like a bear. And taxonomists have been arguing about this for many years. There was the thought that molecular biology might solve the problem, but in fact, if you analyze the DNA of the giant panda, if you look at certain parts of the DNA, it looks more like a bear. If you look at certain other parts of the DNA, it looks more like a raccoon. And so there you are. Classification isn't all that straightforward. You have to think further about some of these things. And then, if you ask further questions, if you say we've classified all these plant and animal species, how did these different species arise? To answer that question, you have to go a little bit beyond what you directly observe and tabulate and get on to some of these other methodologies. So empiricism is not the whole story of scientific method. Well, second on our list of these methods, we have the rationalist method. And René Descartes was the propagandist for the rationalist method back at the dawn of modern science in the 17th century. Rational means reasoning. So this is a brand of scientific method that's going to emphasize reasoning. Start by sitting down and thinking carefully. So you get the image of the scientist sitting in his or her easy chair, perhaps smoking a pipe, Sherlock Holmes style. And according to this point of view, one sits down and thinks about how things must be, how things should be. So it's coming from inside our own heads. Now, the example that Descartes used for this kind of science was geometry. If one, for instance, is talking about the Pythagorean theorem, square of the hypotenuse equal to the sum of the squares of the two sides of the right triangle, Descartes says, would you go about demonstrating the Pythagorean theorem by going out and measuring a whole bunch of triangles and see if they satisfied it? Well, says Descartes, you're going to have measurement errors and you're not going to come up with an exact result. Anyway, why not start from the basic axioms of geometry, very simple, self-evident axioms. All right angles are equal, the whole is greater than or equal to the sum of the parts. Given a point and a line, you can draw a parallel to the given line, and so on. And you can start with these very simple and self-evident axioms, and the way one does in high school geometry, reason to conclusions such as the Pythagorean theorem, all kinds of wonderful conclusions. Isn't this a good way to do science, says Descartes. And so the idea from Descartes' point of view would be to try to fashion all of science on the model of geometry, to find the appropriate basic principles and then reason logically from those principles. Well, this brand of science as the only way to do science rapidly fell into disrepute. How can you do science by sitting in your easy chair and just thinking about the way things must be? However, when it's used with the other methods, it turns out to be very useful and is a continuing part of scientific method, where one is looking for basic principles of science that do have this sort of obvious, clear, and simple character. One such principle is the principle of conservation of energy, that energy is neither created nor destroyed in any natural processes. And this has become really a constitutive principle of science in the same way that Descartes wanted geometrical principles to be a basic part of science. And in fact, when there have been instances of conflict between the principle of conservation of energy as this self-evident principle and observation, sometimes the self-evident principle has won out, at least temporarily. For example, around 1930, in the new field of nuclear physics, they were investigating some nuclear reactions, beta decay, that did not seem to conserve energy. The energy before the beta decay process seemed to be larger than the energy afterwards. Well, how did one deal with that? If one is a strict Baconian empiricist, one says, well, it seems like energy is not being conserved. That's what experiment is telling us. Well, that was not the choice that the physicists of the time made. They said, we really do believe in the principle of conservation of energy because it is so clear and elegant and simple, and one thinks that the universe must be that way. And so, they said, there must be an invisible particle that's going off undetected, which is carrying away the missing energy. Now, of course, your Baconian empiricist says this is just prejudice. You've got to go with what you observe. They said, well, one can make errors, and we really think there's an invisible particle that's going off and carrying off the missing energy. And 25 years later, in 1956, the neutrino was directly detected, and one could see that it was the neutrinos that were carrying off the missing energy. So along with observational data, it turns out that this rationalist approach, where you're looking for these self-evident basic principles, for these elegant and simple and harmonious and symmetrical principles, that also is a continuing part of science. Then there's a third methodology, a third way, the hypothetical methodology. And right away, I think you can see this is about hypotheses, about suppositions, about conjectures. This scientific methodology was a bit of a methodological orphan. Nobody really wanted to claim it at the beginning. Nobody wanted to admit that their science was based on conjectures and suppositions and so on. But in fact, it was used from the dawn of modern science onward, from the 17th century onward. Isaac Newton was one of the people who made use of the hypothetical method very fruitfully, but denied that he was using hypotheses. Well, hypothesis in Greek means supposition or conjecture. This is where you try out ideas. You imagine. Imagination is a part of the hypothetical method. You imagine some possibilities, and then you ask, if these things were true, if my supposition were true, what kinds of consequences would that have for things I might be able to observe directly? This is a kind of approach which has been used to get beyond direct observation. First of all, when you're thinking about things that are very small. If you look at the history of atomism, the notion that matter is made up of very small particles, well, you don't directly observe, or historically one didn't directly observe these small particles. One made suppositions about them and then tried to work from there. Or if you had large and inaccessible things, if you want to talk about the interiors of stars, for example. Well, you can't get to them and see what's going on in there. You have to start by imagining possibilities for what goes on in there. Or if one is talking about the distant past, unfortunately we don't have a time machine. We can't go back and see how geological and biological evolution actually happened hundreds of millions of years ago. And so again, if we want to talk about those things, we've got to begin with our imagination, with suppositions, with conjectures. Now, if this is to be science, the suppositions and the conjectures have to be controlled somehow by observation and experiment. And the way that works, again, is you ask, if this supposition were true, what kinds of things would I expect to see that I can observe? For example, if we start with the beginnings of kinetic molecular theory, if we suppose that the air in this room consists of molecules which are moving around at high speeds, bouncing around on the walls, we can't see these little molecules, so what can we do experimentally? Well, we can say, if we make this assumption, then we can calculate the pressure on the walls of a box that is exerted by these little particles bouncing around. And we can ask, if we change the volume of the box, if we move the walls in so that the collisions with the walls are coming more often, what will that do to the pressure of the gas? And so on the basis of the molecular kinetic hypothesis, one could calculate that the pressure times the volume of a gas should be a constant, that they should vary inversely. Well, one can go out and test that. Robert Boyle did go out and test it back in the 17th century and concluded that observation confirms that the pressure times the volume of the gas is a constant, Boyle's law. And so now that becomes evidence in favor of the kinetic molecular hypothesis, because it is one of the consequences of the kinetic molecular hypothesis. Then moving on into the 19th century, they added some complexity to that. Suppose that the velocity of the gas molecules depends on the temperature, velocity squared proportional to the temperature. Then what kind of a consequence would one expect? One gets the ideal gas law. By calculating that, PV equals nRT, one tests that against pressure and volume and temperature and finds that it tests out very well. So what one gets is evidence in favor of the kinetic molecular hypothesis by testing out its consequences, by testing out the expectations one has on the basis of that theoretical supposition. And that's how the hypothetical methodology works. It's indirect. You're not observing the molecules directly. And then this can be used not only for very small things, it can be used for large and distant things. If one is talking about stellar interiors, for example, one has very well developed theories of stellar interiors, but all on the basis of this kind of indirect evidence where you hypothesize certain things going on in the stellar interior. You ask what should be the consequences for the radiation I do observe coming from the star or from the sun, and then if those tally well, one counts that as evidence in favor of the particular model of the stellar interior. If one goes back into the distant past and asks about organic evolution, again, one doesn't have the time machine to go back and observe that directly, but one can say, if this evolutionary process did take place in a certain way, what would I expect to see in terms of the fossil remains? And then one can go and look at those fossils. What would I expect in terms of the geographical distribution of plant and animal species? And one can check that out. What would I expect in terms of taxonomy, how the different classes of plants and animals relate to each other? One can check out that as well. And these things all tally with the theories of evolution that we are developing, and so count as evidence in favor of those theories. So the hypothetical method then allows us to make progress along the various frontiers where we are moving forward into areas where you can't observe directly. Now, in the case of atomism, in the early years of the 20th century, it in fact did become possible to observe individual atomic level events directly. And at this time, the hypothetical approach that had been developed in the 19th century turned out to be very useful because the theories of atomic and molecular phenomena that had been developed in the hypothetical manner provided a blueprint, a roadmap for the observations that were carried out in the early 20th century that was able to detect atomic level phenomena directly and verify the results of the hypothetical efforts that had been undertaken earlier in the 19th century. So the hypothetical methodology was and continues to be very useful in science. If you look at the science done by a particular scientist or group of scientists in a particular time and place, it turns out that one can analyze their practices in terms of mixtures of these three methodologies: the empiricist direct observation approach, the rationalist thinking about what must be the most elegant and symmetrical and harmonious basic principles for science, and then the hypothetical approach, especially on these frontiers of things that are difficult to observe, imagining and supposing various possibilities and then testing those out by their observable consequences. And so I think the conclusion for scientific method is that there is no prescription for scientific method. You do it exactly this way and that way, but rather we do have these examples which we can classify in terms of three ideal types, and we can analyze scientific method and do science by mixtures of these three different types according to the needs of the specific problems that are being looked at.